So our next presenter is Kanhaiya Lal Chaurasiya from IIT Kanpur, and his topic is pipe health monitoring robot PHMR. Kanhaiya, over to you.
Thank you, Ned. Let me just quickly share my screen. So, greetings everyone. In this session, I'll be talking about pipe health monitoring robots, which are used in the periodic inspection of natural gas pipelines. The principal investigator of this project is Professor Vishak Bhattacharya. And owing to the significance of natural gas in the energy security, this particular project has been termed as project of national importance and is being funded under UAY scheme jointly with GAIL India, who is an industrial partner, which is government-owned company primarily responsible for natural gas processing and distribution in India, along with Ministry of Education. So, moving further, just a very brief introduction about myself. I have completed my Bachelor and Master of Technology in the Department of Mechanical Engineering at IIT Kanpur under a dual degree program in 2016. Later on, I have industrial experience with Tata Motors Limited, which is an Indian multinational automotive company, where I have worked in the defense and commercial vehicle segments. And currently, I am associated with SMSS Laboratory as a senior project engineer. My research interests and projects are primarily in the domain of structural health monitoring and shape memory alloy-based actuation systems. So let's talk about the context and motivation behind this project. In fact, the development of a country is measured by its energy use and accessibility, which in turn depends upon the complexity of pipeline network present in the nation. In fact, the impact and importance of energy are beyond the geographical boundaries in the contemporary context. There are transnational pipelines projects such as Nord Stream between Russia and Germany. Currently, you must be knowing that their second version, Nord Stream 2, is halted because of this ongoing conflict. So ultimately, these transnational pipelines are so important that we have with our neighboring countries, TAPI network pipelines, which is spanning over geographies of 4 nations and catering to their energy needs, which is the Trans-Afghanistan pipeline. Therefore, in a nutshell, pipelines have become the key components to transfer fluids such as oil and gas over a long distance. In India itself, over 13,000 kilometers of oil and gas pipelines have been installed at the end of 2021. And this number is further expected to be 28,000 by the end of 2030. To maintain this huge pipeline network, there are chances that pipeline failures and ruptures can happen, which can be seriously catastrophic and may result in significant economic or human loss. In the open literature, it has been reported, and from several reports, it has been shown that from 2010 to 2018, a total of 1969 accidents of oil and gas pipelines are reported worldwide. These accidents caused close to 400 injuries and fatalities, as well as incurred a cost of almost $500 million. So the most common cause of the failure are reported to be corrosions, as well as cracks, as well as dents and deposits and metal loss on the pipeline surfaces. These failures contribute to the weakening of the structure of the pipeline and ultimately leads to the burst. And as we can see, there are catastrophes which leads to both human as well as economic losses. So the project aims at developing a pipe inspection robot to maintain the integrity and operability of the pipeline by scanning the inner surface of a pipeline network using suitable sensory system and preparing a real-time inspection report of the same. So with that, let's look at the existing solution that we have. There are solutions available in the market which goes by the name of PIGS, which is a pipeline inspection gauges. Their design is based on the polyurethane-based spherical discs, as you can see here. These spherical discs or cups have been made in such a manner that they work on the principle of block flow condition, which means the gas flow will be completely blocked once it is inserted into a pipe section. and they are propelled due to a pressure difference between their nose and tail. So due to this block flow condition, it suffers with two major disadvantages. First of all, by virtue of its design, it disturbs the fuel supply. Once the inspection operation is started, the gas distribution in the main as well as subsidiary networks will remain halted throughout. And secondly, it has been reported in the open literature by many researchers that this kind of system generates dry friction induced chatter vibration, because their entire surface remains in touch with internal surface of the pipeline during motion, and thus are known to jeopardize the health of pipeline itself. So, and also not only this, these companies generally do not sell the complete robot itself. Instead, they provide inspection services, which we call pigging. So at a rate something close to $100 per kilometer, which can prove very costly to the business units. So to cater all these challenges and shortcomings, at SMSS Lab IIT Kanpur, we have developed an 8-inch pipeline network, which typically simulates the gas pipeline network that is laid on the country. And together with one of the pioneer companies in gas transportation, GAIL India Limited, we have taken the challenge for design and development of an array of high precision, cost effective pipeline health monitoring system, which are based on smart sensors, which is integrated with efficient data communication. So the system that you are looking currently at has an optimum design of robot chassis with 4 modules, with a total weight of 16 kgs and an overall length span of 1.25 meter. It can pass through several bends such as 90-degree bends, complex S-type vertical bend, as well as horizontal bends. So let's talk about each and every unique features of the system. First, we'll move into the deflection system. So unlike conventional pigging robots, which are propelled by a pressure difference created across the robot, the new robot being designed in such a manner that it is propelled by the drag force due to flowing air. The deflector shown into the picture takes the pressure of the gas and generates the drag force. And by virtue of its design, it takes care of the two disadvantages of the conventional pig system. In this system, only the wheels, as you can see, it is a wheel-based system, unlike the previous or conventional spherical or disc-based system. In this system, only the wheel touches the pipeline, and hence, and it has been tested experimentally that the frequency of the vibration is nowhere near to the natural frequency of the pipeline. Thus, the deflection system is better for smooth drag force generation as well as running of the system. This deflector has also 3 bypass vents in it, so that the drag force can be controlled, and hence the speed of the robot can also be governed in such a manner. The next innovation is in terms of speed control system. This is passive system which harnesses kinetic energy of the system. It has a combination of hydraulic system, motion transmission, and brake system. So being passive in nature, it harnesses kinetic energy of the system to actuate the hydraulic unit, which ultimately applies the brake when robot is moving at high operating speed, and thus in this manner it governs the speed automatically. Once again, in another scenario, if the robot is moving at a lower speed, then the hydraulic brake is released, and the robot moves at a slightly higher operating speed. In this way, the scanning of the pipe surface with several sensors mounted on it are done in a uniform and smooth manner. Next, we'll move on to another segment which houses the infrared-based optical sensing system. The proposed optical sensor method is based on the absorption of reflected infrared waves and utilization of the phototransistor as a detector. This method essentially contains an infrared emitter and receiver. So the reflected ray is measured to detect the anomalies in the pipeline. When the surface is smooth, all the reflected rays will be received by the receiver. And when there is an undulation happening, so this reflected ray is measured to detect the anomalies into the pipelines. These sensors, as you can see here, it is surrounded all around the disk to get the distributed picture of the damage on the circumference of the pipe. This sensor is unique addition to pipe health monitoring robot, because generally what happens, conventional pipe inspection gauges come with only magnetic based sensing system. But if imagine a scenario if a pipeline is non-magnetic in nature, like polymer based pipelines, in such cases these optical based sensing system works very well. And moving on to the next segment, we have a second most important touch sensor. So it touches the pipeline as it moves, and we have currently six such sensors mounted on the robot. These sensors record how the pipeline is having different types of undulations into it. So as these undulations change the vibration characteristics in the touch probe, which encompasses, which has a piezoelectric crystal embedded in it, it starts to change signals. And from that vibrations and from that electrical signal, the positive or negative anomalies into the system can be interpreted. The next segment we have in our robot is having the magnetic flux leakage sensors in it. We have currently 4 such distributed sensors with magnets on the robot, which generates a magnetic field line all around the pipeline. Since it is a proof of concept module, that is why we have 4 modules at a 90-degree separation. In further developments, we have envisaged a full 360-degree module so that it can give us the picture of completely circumferential image of the pipeline. And imagine if there is a crack or anomaly present on the pipe surface, then this magnetic flux get disturbed. And we have giant magnetoresistive sensor as well as Hall sensors, which picks up the disturbances in these magnetic flux sensors, which plugs the which basically picks up the magnetic flux disturbances or leakages, what we call it, which then further be interpreted in terms of crack or anomalies in the pipe surface. And finally, we have the very final module, which has a spring damper system. And that works like a shock absorber, which absorbs the impact energy to save the robot from an unlikely collision. So in a nutshell, this is the entire robotic system that we have developed. And moving on to our next segment, we have also performed several multi-body simulations to establish the contact forces, the friction forces, and the joint forces in such a manner that we need to so that the design and the design can be optimized, and based on these simulation results, we have designed our chassis in a modular fashion. These modular designs enables the robot to pass through 90-degree bend as well as other complex bends. And both 2D and 3D analysis have also been performed in ANSYS Workbench to understand the fluid structure analysis, fluid structure interaction in a better way. And these simulations actually helped to understand the dynamic of our system and provided a platform to optimize the design parameters accordingly. Coming to the sensor architecture, in this particular figure, we can see how the subcomponent of electronic system are integrated and connected to each other. As you can see, we have all the 3 sensors which are used for scanning the pipe surface, along with the rotary encoder, which actually captures the speed of the robot in a real time. All of them then sent to a signal conditioning unit and then have been further transferred to a data acquisition system. In this system, we have one onboard storage unit which can store all the defect acquisition, all the defect data as well as the speed data, and then it can transfer the in real time to help track the robot into the pipeline. And there are other protection circuitries and batteries which completes the overall circuitry. When we transfer the data from one end to other, we have also developed a custom graphical user interface to monitor as well as inspect the sensor data. In the left side, you can see we can in the real time look into the velocity and distance traveled by our robot into the pipeline network. And on the right side, we have two interfaces in which once the inspection is completed, we have the data with us, all the sensors data. And suppose we want to inspect each and every sensor or the combination of sensors for comparative analysis, we can perform the same in this interface. And towards the end, it generates a real time, it generates the inspection report for further investigation and for further references. So this is a Python based GUI that we have developed for specifically for this robot. And coming to the in-house test bed facility, we have at IIT Kanpur in the Department of Mechanical Engineering, we have this 8-inch based pipeline where, as you can see, this is a launching station and this is a receiving station. We have a semi-loop 60-meter pipeline with a compressor having a 12 bar capacity. This particular pipeline has several bends incorporated into it to check the maneuverability of robots design. And we have also artificially planted several defects at periodic intervals to test our robots and our sensors into this system. So we will, in the upcoming section, I will show the results of all the sensor and data of a particular trial run. And these are the experimental results of MFL sensor as well as touch probe sensor. To actually precisely detect the dimension as well as position of the defect into the pipeline. So there are, in a broad category, we can say there are two kinds of defect. One is the positive anomaly and another is negative. Positive means those defects which has kind of a metal deposition into it are convex defects, and those having negative anomalies consists of cracks, metal loss, maybe pinholes, dents, all these things. So our sensors are very much capable of capturing the dimension as well as location of the defect into the pipeline. And these research findings are published in the Journal of Natural Gas and Science Engineering, which is a peer-reviewed international journal. And in the next segment, I will showcase one sensor data from the trial run that we have conducted. So this is the outlay of a 60-meter semi-loop pipeline, which is having several flanges which connects the two pipeline section, as well as there are defects which has been planted in the form of dents, in the form of metal loss, in the form of corrosions. So all the fluctuating signal that you see from the MFL sensor corresponds to each and every defect that we see on the pipeline, both on the external as well as in the internal surface. So this kind of data we get from the MFL touch probe as well as optical sensor, and we then generate a report as well as analyze in the custom developed graphical user interface. And coming to the important point of market access and research impact, there are several important factors that drive the global pipeline pigging industry, such as growth in cracks and leakages in gas pipelines, as well as there are stringent government regulations for safety and monitoring. And in the report published in the Grandview Research, it has been found that Asia Pacific is estimated to be the fastest growing region with a compound annual growth rate of more than 7% over the forecasted period. So with a growing energy demand within several sectors in India in recent years, these demands will definitely bolster the gas industry growth in coming years, which will eventually drive the market in Asia Pacific region. So this is estimated to create an ample of opportunities for in-pipe inspection robots in the Indian as well as Asian markets. So coming out to the research impact part, the PHMR that we have developed is based on the indigenous technology, has overcome the shortcomings of conventional PIC systems, is very cost effective as compared to the services provided by multinational inspection companies, and has commercial potential to be commercialized in the Indian as well as global market. So Thus, the proposed or the developed pipe health monitoring robot serves as a better cost-effective solution than the existing health monitoring inspection services. To that extent, we have filed patents. We have filed 2 patents. One is the design of the complete robotic unit, and other is specifically to the speed control system, because this speed control system is very unique and is not found in any of the pipe inspection gauges available in the market. Along with that, we have we have some we have published our research findings in 2 international journals in Sensors as well as Journal of Natural Gas and Science Engineering. And with this final short demo, I would like to end our presentation. In this short demo, I will showcase our robot running into the system, as well as the overall in-house facility that we will be having in the Department of Mechanical. So thank you for your time, and I take this opportunity to thank the symposium organizers and conveners for providing me the platform to showcase our research to the scientific community. Thank you very much.
Thank you for the nice presentation, Kanhaiya. Now, may I request other members to have, if you have any questions, you can ask. Okay, I will ask one question.
Sure.
How you are monitoring the distance travel?
So we have installed a rotary encoder onto a wheels of the system, and that rotary encoder captures the rotation has been converted to a linear velocity, and
Yes.
that linear velocity is being transferred over wireless transmission to our graphical user interface, which then converts this signal into a graphical tracking.
Okay. Well, in that
can I ask a question?
Yes,
can you hear me?
Yeah, I can.
Yeah. So this device can detect the problems in the pipes. Can you add some tools to fix these errors, or is this allowed to? Or do you think
it is kind of a health monitoring. So the overall objective of this robot is to conduct a periodic inspection, so that any timely action can be taken by the engineers and authorities who are into the maintaining of this pipeline. So maybe let's say if a crack is happening, so we can track the progress of the crack, and when it falls or when it reaches to a point where it is very critical, then that section can be taken care with the respective manufacturing or material science specialists.
I see. Okay.
I have one more question.
Yeah, yes.
If you have used odometer, so possibly if the wheel slips, then there is a chance of data loss or
right.
So in that case, have you thought of something?
So yes, we do not rely on the odometer on only one wheels. We have a design provision for this rotary encoder on 3 wheels.
Okay.
So in case if any wheels get ruptured, or let's say, as you mentioned, slips, the data from other wheels will take care of the real-time inspection.
Yeah, thank you. Thank you.
Thank you. Thank you, everyone.